Today, we're going to dive into a book that is, no exaggeration, a legend in the software world. Joshua Bloch's Effective Java. This isn't just a book about syntax or rules, it's really about the philosophy behind writing code that's not just good but truly great.
So let's start with the big question. What's the secret sauce? What's that line that separates code that just works from code that is elegant, robust, and a joy to maintain? Is it about some complex algorithm or the latest fancy feature? Well, Effective Java argues it's something way more fundamental.
And the answer is this. It's not magic. It's about craftsmanship. Great code is built, not just written. It's the result of deliberate, thoughtful choices and a deep understanding of your tools. It's about treating software development like a craft, and this book is basically the master craftsman's handbook.
And that craft starts small. I mean, really small, at the level of the individual building blocks of our programs, our objects and classes. Because let's be real, if your bricks are crumbly, the whole building is going to be unstable, right?
Here's a perfect example right out of the gate. Instead of always defaulting to a standard constructor to create an object, the book pushes us towards something called static factory methods. Why? Well, they're just more flexible. For one, they have names, which can make your code way easier to read. And unlike constructors, they don't have to create a brand new object every single time. They can return a cached, pre-existing one, which, let me tell you, can be a massive win for performance.
Now here is one of the most powerful ideas in the entire book for building reliable code: immutability. An immutable object is one whose state can't be changed after you create it. Think about a string in Java for a second. You can't actually change it. You only ever create new ones. This isn't a limitation, it's a superpower. And the benefits are huge. Immutable objects are just simpler. You never have to lie awake at night wondering who might be changing its state from some other part of the program. This makes them automatically safe to use in multi-threaded code without any complicated locks, and you can pass them around your system with total confidence. They are the absolute bedrock of reliable software. Building solid foundations also means you have to play by the rules of the language. There are fundamental contracts, like the one between the equals method and the hashcode method. If you change what it means for two of your objects to be equal, you must also change how its hashcode is calculated. If you break this contract, your objects will just start behaving bizarrely in things like hash maps, and you'll have a nightmare of a bug to track down.
Okay, so we've got our solid, reliable building blocks. What's next? Well, now we have to assemble them. And we need to build systems that aren't just solid today, but are flexible enough to adapt to the changes that we know are coming tomorrow.
All right, this next one, this is probably one of the most famous pieces of advice in the history of software design. While inheritance is often the first thing we learn in object-oriented programming, Effective Java issues a serious warning. It can be a trap. Inheritance is like a family tree. It's rigid. You're locked into your ancestry, for better or worse. There's a classic example in Java's own library, where the properties class inherited from hashtable. This accidentally exposed methods that allowed people to break a core rule of properties objects. Composition, on the other hand, is like building with Legos. You build bigger things by plugging smaller, independent things together. It's flexible, it's robust, and it's a much better way to reuse code. And here's the other half of that design for change philosophy. Your code should depend on abstractions, on the what, not on the concrete details of how. So instead of declaring a variable as, say, a hash map, you should declare it as a map.
Why is this such a big deal? Because it makes your system incredibly flexible. If you decide 6 months from now that a linked hash map is actually a better choice for performance, you only have to change the one line where that object is created. The rest of your code, it doesn't care. It just knows it's talking to a map. This is how you build large systems that can actually evolve without breaking.
Okay, so we've got solid components, and we've assembled them into flexible systems. The third, and you could argue the most important principle is this. Remember that code is read way more often than it's written. We have to optimize for human understanding. This right here uses a really simple method to make a really deep point. You know how sometimes you print an object, and it just gives you a bunch of gobbledygook? Well, the official rule for the toString method says you should provide something a human can actually read. It's a small thing, but it shows a profound respect for the next developer or your future self who has to debug that code. This slide shows that evolution perfectly. We used to use integers to represent things, like suits in a deck of cards, but nothing stops you from accidentally passing in the wrong number. So then we tried strings, but a simple typo could create a really nasty bug. And then enum types came along. Game changer. They're type-safe, they're readable, they're powerful. It's a perfect example of a language evolving to help us write better, more human-friendly code. But writing for humans isn't just about making things easy to read. It's also about making them safe to use. It means actively avoiding features that hide enormous, terrifying risks.
Let's talk about Java's serialization. On the surface, it seems handy, right? A way to turn an object into a stream of bytes to save it or send it over a network. But the fundamental problem is that it's like a magic trapdoor into your system. An attacker can craft a special stream of bytes that makes your application create almost any kind of object, leading to a massive, nearly impossible to defend security hole.
And this is not some theoretical problem. In 2016, a ransomware attack used this exact type of vulnerability to shut down the San Francisco public transit fare collection system for 2 entire days.
So the book's conclusion on this is, well, it's about as blunt as you can get. The advice is simple. Just don't use it. Ever. Not in new systems, the risk is just too high, and modern alternatives like JSON are way safer. Writing for humans means protecting them from these hidden traps.
So when you put all these principles together, what do you get? You get a completely different way of looking at code. It's a fundamental shift from just getting something to work to consciously practicing a craft.
The craftsman's code is built on a foundation of solid, immutable components. It's designed for change, using flexible composition instead of rigid inheritance. And above all, it's written with clarity and safety in mind, because the craftsman knows another human being has to read it.
And that's really the heart of it all. When you boil it all down, effective Java is about writing code with empathy. Empathy for your teammates who have to work with your code, empathy for your users, and maybe most importantly, empathy for your future self who has to come back and fix a bug in 6 months.
And that really brings us to the end, because the real value here isn't just knowing these ideas, it's about actually doing them. So I'll leave you with a challenge. The next time you sit down to write code, what's the one principle from all of this that you're going to apply?